Good evening and welcome everybody. It's Obi-Wan Pez. This is N Simplex Pachinko. Tonight, gonna talk about all sorts of mathy type stuff. Anybody is interested in giving some sort of problems in order to work them out on stream, can give it a shot. Otherwise, we can talk a little bit about pedagogy and like mathy, how to teach. Structure of classes and things like that. I don't know. We'll see how things go. I was reminded I picked up a copy of Elementary Algebra by Harold R. Jacobs many years ago. I actually picked this up as an example of a textbook that was like a little more off the beaten path, but accepted by like everybody. I was doing a class called Reading in the Content Area, and so they said, find a book from your field and let's come together and talk about it. As it happened, both of the Jacobs books, Elementary Algebra and Geometry, are very engaging and helped kind of make me think, at least, that there was more to making a nice math book, like a textbook, other than just like doing the kind of throw out a mostly historical account of what happened, say exactly how you make it work, and then throw out some practice problems. So in the book, Jacobs starts with a licensed comic strip, and it's like on every basically third or fifth page he's got one. So a lot of them are in public domain, so that's okay. And then goes into an explanation of like kind of what's your intuitive sense of how things work. So the introduction is called A Number Trick. So think of a number from 1 to 10, add 7 to it, multiply the result by 2, subtract 4, divide by 2, subtract the number you first thought of. Is your answer 5? And of course, the answer is, well, yes, it is 5. How did you know that? And so, like, pretty much anybody who's studied basic algebra knows the idea and has seen these kinds of mathemagic tricks before. Any of the new students out there may not understand exactly how it works, but like clearly there's something going on. So I figured, why not? Let's just throw it out there. So we had think of a number. Add 7 to it. Yes, there were restrictions on there were restrictions on like, oh, think of a number from 1 to 10, but realistically, it doesn't matter what number you think of. It's always going to work. So here's why, right? Add 7 to the number you thought of. Multiply that result by 2. Subtract 4. Divide that result by 2. And then subtract the number you first thought of. So in this particular case, right, we've got all these individual steps that we can work through to say, like, how does it change? So if we were to expand this out, we would see that we would get on top a 2x plus 14 minus 4 all over 2, and then subtract x from all of it. Here we have 2x minus plus 14 minus 4 is going to be plus 10, all of that's divided by 2, and then we subtract x. Here we divide each individual part, so 2x over 2 plus 10 over 2 minus x, and x plus 5 minus x is, of course, going to get us 5. The best and smartest of these tricks do not explicitly tell you to, like, undo two operations exactly the same as each other. So this particular one does have a multiplication of 2 and a division by 2 in two different places, but they're far enough apart where you're not really thinking about it. And then further, if we're adding 7 and subtracting 4, like, how do we get 5 at the end? That's crazy. But we know that it's through the multiplication, subtraction, and division of those numbers that now we can see, oh, well, the 7 gets multiplied by 2 becomes 14. We subtract the 4, becomes 10, and then divide that by 2, it becomes 5. And then we just clear out all the stuff around it. So Jacobs goes on to say that from that point, how does this trick work? And if we make a table, like, and he lists out a whole bunch of results, like, what exactly works? Is it step by step? Yeah. What exactly is happening step by step to make 5 show up at the end? And, like, you could see the individual patterns going all the way across. Whoa. Right there. Alright, so then, underneath it, and again, keep in mind, this is for algebra students who have probably not been exposed to necessarily the methods of algebra up until this point. Maybe they've heard of it, maybe they've done some, I know my parents, for example, really loved asking me math questions in the car. So, and once they exhausted all of the, like, what's this plus this and what's that minus that, they did eventually start with the, like, what plus 7 is going to get me 6, you know. Not that one. There is a simple way to discover the secret. Instead of writing down a specific number, we write the symbol, which we're just going to make it a box. And for us, obviously, we just use x because, you know, unknown values can just be variables. So introduction of the variable is the same as I probably would have thought in, like, elementary school. Use a, you know, use an empty box, use a question mark, use like a symbol that represents it. Don't immediately start with x because people get intimidated for some reason. Sandy does a series of, or the exact series of steps that are in there. And says, okay, on each individual step, we're going to take, you know, the path of add 7, so we add 7 little dots, and then multiply by 2, so we double the number of rows that there are, just copy paste, right? Subtract 4, take away 4 of the dots, divide by 2, cut it in half, and then subtract the number you first thought of, which is the box, the x, and all we're left with is 5 single dots. So, and the exercises in this one basically are like, you know, try a few more of these number tricks that I can show you, and then make your own. Right. So, with anybody who might be here, we have a central repository. That is not what I want. There we go. Okay, so we do have a central repository. We've been using Penn Center's Discord, and in it, he also uses a maths forum and maths chat section, so if you're at all interested in putting some questions in there, feel free. And I will be able to get to them as soon as I can. We'll also pop up on a couple of the we'll also pop up with a few of the mathematics educator, AMATIC, American Mathematical Association, to your colleges questions, and see what else might be interesting. I don't think we're going to run out of material here, but, you know, might get bored. So, okay. Sensation! How's it going? Death to the west. Oh no. Let's see. Well, you know, it's only the 2nd of July. I guess I'm not necessarily going to be on the 4th, so, you know, got to get it in when you can. So how you doing today? Okay. Now we can actually start doing stuff. So we were talking about Harold Jacobs' elementary algebra. This is an edition from 1979, which I purchased in 2006. This actual book was printed not then. It felt brand new. I mean, it still feels brand new because I never use it. But it's on the 14th printing, and apparently there is a revised edition that's out these days. But nonetheless. So I purchased this as a result of joining a class at my local community college back when I was in Maryland. In fact, the same place that I worked eventually. And it was called Reading in the Content Area. So how do you get students, how do we as educators read our textbooks and try to get students to understand like how to read it. And I was one of 3 people. There were 2 classes. I was one of 2 people who were math teachers in the first class, and one of 3 in the second class. The same person in both of them, who was a math person, was highly skeptical that any of this would ever possibly be necessary. Why would we need reading in math? Goodness, have you tried reading math textbooks? And I was like, that's kind of the point. And then we had a third guy who was from, at the time, it was the Democratic Republic of Congo. What do we have now? Yeah, I think we're still Democratic Republic of Congo. So he said that like there was a significant problem, especially in 06, 07, when like he said, well, it depends on who's in charge this week. Might be called Congo, might be called Democratic Republic of Congo, might be called Zaire again. I was like, oh no. I used to be good at geography. We haven't kept that much in touch, but he is doing wonderfully as a math teacher and a father. His kids are, I think, between mine. So, you know, we see each other on Facebook, but he was like, we absolutely need this. Let me tell you why, and came up with like 20 different situations in which we needed reading in the content area. I was like, we're going to hang out. We're going to get along. So, like, the 2 of us sat next to each other in class every single week and just, like, came up with, like, throwing ideas off of each other, and the teacher's like, oh my god, this is amazing. And then the third guy, eventually, we finally got him, where he was just like, huh, yeah, I do see value in this. And I was like, yes. Between me, and not to downplay anybody else's role, but, you know, me, the guy who was enthusiastic, and the teacher, like, all 3 of us had to work together our absolute hardest to convert this one guy. And I mean, it's not like you should be spending half of your contact hours teaching kids how to read math textbooks. That's not it at all. But it's how do you get math students to become better readers of math? And so it was a real useful class to then say, like, you know, how am I framing my assignments? How am I framing my exams in such a way that I'm making my students better readers? It's super, super, super important eventually that, you know, we get our students to understand how to read in our subject. Okay, there we go. I'm gonna get that off my screen. So I did look it up. I was all prepared to be like, oh no, did Harold Jacobs die? But no. He is 85 and doing well. Last time I actually contacted him after buying this book, and like asked if there was a particular, method to use, if he, like, I came up with probably 30 questions, but keep in mind this was 20 years ago, so I came up with a whole bunch of questions that, like, how do I most effectively use your book, essentially? And he contacted me back, like, the next day. Granted, he was approximately 65, probably retired-ish. And, like, very nicely went through my entire series of questions and answered every single one of them to my satisfaction. And so I emailed him back and just said, "That is wonderful, thank you so much." And he was like, "Oh yeah, no problem, thanks for buying the books." I also have, in addition to his, I think, you know what? I think he sent me the teacher's guide for it, for geometry. So I think after I emailed him, he sent me this for free. I didn't ask for it. It wasn't like, oh, I'm desperate. No. He was just like, let me send this to you, because it's got some good stuff that's not just like, here's how you solve the problem. It's also like, here's some work on how to introduce the topics. This one's geometry, obviously. Well, don't lose the book. But, yep. Geometry, Seeing, Doing, Understanding, 3rd edition. New to this edition, more focus on informal and paragraph proofs reflecting current NCTM standards and recommendations. Standard, current asterisk being 2006. So, oh, and both of these books have the stamp in the front of it. This book is the property of, with the, this is like the exact same thing that we used in school. It's just got like line by line. This book is the property of state, province, country, parish, school district, book number, issued to, you put your name, year used, condition, issued, and returned. So it amuses me to no end that, like, somebody still uses that. And 3rd edition of Mathematics, A Human Endeavor. So this was one that I purchased after starting my honors seminar that I was doing. This one, original copyright 1970, reissued 1994 as 3rd edition. So this is approximately 1995, But this goes through a lot of interesting goldfish situation. Anybody who knows Critical Role? We're just gonna go over here. Boop. Anyway, yeah, different types of symmetry, different types of like looking at the Fibonacci sequence in nature. There's all sorts of cool stuff in that one. So, Mathematics, A Human Endeavor is a pretty decent, like, how to appreciate math kind of book. At the beginning of Lesson 1, Addition, he has the art and quote from Lewis Carroll's Through the Looking Glass. "Can you do addition?" the White Queen asked. "What's 1 and 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 1? "I don't know," said Alice. "I lost count." With the immediate point, soon after a child is able to count, he learns how to add. So, Astacon! Very good time zone to you, sir. Thank you for the lurks. Great! We're looking at Harold Jacobs' Elementary Algebra and talking about different kinds of aspects of math that are here and some of the pedagogy that might go into it. So thank you very much for sticking around. The two operations are closely connected, as anyone who has ever added by counting on their fingers knows. Consider the problem of adding numbers represented by two sets of circles, so 5 circles and 2 circles. At first, a child finds the answer by counting all the circles. Then, they learn the fact that 5 plus 2 is 7. So, this is also an interesting point, is there is a heavy push right now to go back to basics, as it were, with a lot of the mathematical pedagogy. And so, typically what you have is you have the you have a lot of people who are, let's say, politically left-leaning, who might say that, you know, this is going to be a better way to expose somebody to this idea of moving things around and trying to generalize the idea that we can put symbols to this. Get somebody to develop an innate concept. Some people might argue that this should have been done in kindergarten or at home, and therefore it like has no place in the first grade classroom or whatever. But the kindergarten, first grade is really the first time that students have like the formalization of class ideas given to them. So not everybody's at the same level, not everybody's at the same speed. So you do have to start from absolute basics. And a lot of the people that I've seen who advocate for return to basics are saying, like, this will be sufficient. And ad nauseum, if you will. We're simply telling facts about things should be sufficient to teach someone mathematics. And I disagree. Now, I will say that is not to say that everybody thinks that way. There are many who say, like, well, no, the first time that you get a student to get into here, that's what you want to be doing. But a lot of the, like, Common Core type stuff in mathematics, especially with the especially with communities that are getting into Common Core and being like, okay, let's get a more interesting look at this and not just tell students facts and make them memorize stuff. when they get to the time when it might be appropriate to just give them a table and say, here are the facts, they don't want to do that. And I can respect it because, one, it promotes literacy, mathematically wise, to have both of these things there. It is also an accessibility issue. If you have somebody who does not understand English notation and all this, you can't throw this at them and expect them to just be happy with it. It would be extremely helpful if you could provide alongside of it something like this. Give a child a fish, they will smell a fish. Teach a child a fish, they might fall into the river. Yes. But, you know, the point of accessibility and all of this, you know, diversification of knowledge, generalizing it to a much larger extent, does not have to be some weird, big, scary thing to communities that are like, well, you know, this table was good enough for me, so it should be good enough for my kids. Like, it doesn't have to be scary. We can all agree that if you put this stuff with this stuff, then it enhances the knowledge and makes the students able to better understand what's going on. And I'm saying that very, you know, simply, but this is on a very simple topic. So we're looking at doing the same thing for things like, let's do plus. Right, so like 3x plus 4 equals 5. Well, that's the same as taking 3 sticks that we call x and 4 blocks, and then saying that this is going to be the same as 5 blocks. So, my goodness, whatever shall we do? Okay, well, we know that this equality sign here is essentially like this is going to work. It's fine. Is essentially like a big pan balance. Currently, it is balanced. We would like to keep it that way. So what do we have to do? Well, we have to take off things that are the same from either side, or add things that are the same on either side in order to make them better. So here we just remove pairs of singles, and then eventually we end up with this, which ends up being, oh look, that's 3 x's over here, and that's the same as 1 over here. Right, so then what can we do? Well, if this is like a chunk of butter or something, we could take that chunk of butter and then split it into however many pieces we need. It'd be really convenient if we could chop it into 3 pieces. So over here we can subdivide and then say, okay, well, that leaves us with whatever. It's fine. It's all fine. Right, the little sliver that we left behind, and then we take off 2 of those other ones. Well, as it turns out, right, then one of these x's is going to be now 1 there was one piece originally that was split into 3 pieces. So each is going to be worth 1/3, right? So then we get here, this 1/3 here, and this 1/3 here. And as we take off those x's, the 2 x's from one side, because we divided by 3, we take off 2 of the 1/3 from the other side, because again, we divided that by 3 as well, and we're left with that x is going to be 1/3. So we can work with an intuitive sense of how all of this stuff works. We don't need to explicitly go 100% with the algebraic approach every single time the first time. Be much cooler if we could have, like, you know, objects with variable weight that you could just, like, throw on there. I mean, you could literally grab different objects, but it'd be cool if you could just, like, set it to, I want this thing to weigh 1 kilo. Maybe someday. Anti-grav. Woo! And an increased grav. Alright. So then on this page, Jacobs is saying, okay, we've got, you know, these 2 things. We could also represent the original addition up here, not just as like objects that are being moved around, but also as distances. Pretend those are the same. Right, so like each of these is going to be 1. And then here we had, okay, well, this was 5 and this was 2. So this is like going 1, 2, 3, 4, 5 for the first one. Or it's worth 5, depending on how you want to frame it, depending on how students are getting it, right? And then we also have a 1, 2 on this other side. And when we put them together, aka add them, then this is going to be then the position 1, 2, 3, 4, 5, 6, 7. And again, we could see that this distance is equivalent to the values that we're getting from these things. So having this diversity of thought and having this diversity of methods of approaching something is like the #1 key thing for anybody who is ever going to be joining the ranks of the educators. I don't care even what subject you're teaching. Having a variety of approaches is going to be the most valuable skill that you will ever develop. Science teacher, right? You want to debunk flat Earth? You better have an experiment for every occasion. Science, yes. Do I have one? Gotta have one somewhere. No. Oh well. I know Anna Demetriou is also a good one. What is it? Yeah, she has an audio clip of her just screaming, "For science!" Or it was for science, I think. right? And then Jacobs expands the idea and says, okay, well, if we want to replace those squares of unknown numbers with x's, y's, all sorts of other letters, let's do it. We can do whatever we feel like. So his example is that next what we do is we say, okay, if we're going to do this distance thing, we could say, all right, we got a distance of 4 here, and then some unknown distance, which then comes after that, and then maybe another 2 after that. So what does this mean in terms of like mathematical stuff that we were just talking about, right? We generalize, we expand the attempt to say, like, what is it all about? So now we say, well, this is 4 plus x plus 2. And thinking about distance, right? Does it really matter in what order we add these things? Does it matter where overall the endings of these are? If it's something like a compass course, you know, you're probably turning at these, so it does actually matter, right? Like which ones come first and which ones come second. But if you're just going in the exact same direction all the time, then it doesn't matter which one is first or second or third. We could have them in any order we want, and we end up in the same place eventually. Right, so we could go like this. We could have 2 here, and then 4 here, and then our x here. And provided I actually drew them to scale, which I did not, then we'd end up at the exact same place at the end. And again, we could prove this by going through and checking it, or we can also then talk about the commutativity of real numbers. So in terms of commutativity, the commutative property says that if you have real numbers which are being added together, then it doesn't matter in what order you're adding them. You can add them together in whatever way you feel comfortable, and it will be equivalent no matter what. So we actually did this on Lean, the natural number game. So when we looked at the natural number game, there was somewhere in Edition World. Yep, additive commutativity. We said, okay, let's do an induction. So induction proofs say that if we start with a particular set of axioms, a particular set of properties that we know to be true, and then, sorry about the light, by the way, if that was very intense. Start with a base case, and then say, on all subsequent cases, we're just going to see what's going to happen, right? And then we'll prove that if we assume that it's true in this particular case, and then prove that it's good for the next one, then it doesn't matter where we started. It's good for the one we started at, and then the next one is going to be gotten from the proof that we just wrote. Imaginary numbers matter which way around their position when added together. So for that one, not really either. But it depends on what you're looking at, right? So if you have a series of vectors, and complex numbers are easily done using vectors as well. So if we ended up doing something like this and saying we have 1 plus 3i, 4 plus I, and 2 minus 2i, If we went like this, what we could do is say, okay, 1 plus 3i can look like this. 4 plus I, that is the wrong way around. Wow. I study math. 1 plus 3i can look like this. Okay, 4 plus I can look like this. And 2 minus 2i can look like this. Now, if I reorder the way in which these are done, I will actually end up back in the same place. So this is 2 minus 2i. This is 4 plus I. And this one is not quite, but close enough. 1 plus 3i. Now, I could have done that in any order. And, what is it? The proof of which is left to the viewer, as an exercise to the viewer. So you can put them in any order you want, and you will end up at the exact same location. However, the intermediate points, right, are going to be different from each other depending on which ones you put first and second and third. So, why, thank you. A lot of practice. So if we did, again, 2 minus 2i, and then change it up and do 1 plus 3i next, we'd end up here, give or take, and then 4 plus I. Again, we end in the same place, but then this ends up here instead. Or, and I think you might be able to see it, if we go 1 plus 3i and then 2 minus 2i, and then 4 plus I. Or if we went 4 plus I first, followed by, not far enough, there, followed by 1 plus 3i, or followed by 2 minus 2i. Anybody see it? Even better, it is a polyhedron. Right, this is actually a like rhombic prism. No, it's not rhombic. A parallelepiped, I think, is the appropriate name for it. Yep, 3D shape whose faces are all parallelograms. Yep. So it's as if we took a cuboid sort of shape and like kind of tilted it like a bad house. And interestingly enough, right, we can actually do a coordinate shift, which could cause all of the intersections to become right angles. And so we could, using a coordinate shift, we could end up with a rectangular prism because the sides are all different sizes. So it's just basically a cube that's been stretched out a bit and then tilted into a particular direction. And this actually is where like shifting based on vectors, is actually where we get a couple of really cool stuff, a really cool couple of pieces from differential equations, which, by the way, if anyone is interested in learning differential equations, I am trying to host a class on differential equations starting next week. We're going to be working on Penn Center's Discord server. I have a section available for anyone who's interested in signing up for it. Currently, we have one student by the name of Zach, who is e to the 2i pi, who is also one of our esteemed math streamers, and was, possibly still is, doing his math stream. Yep, still doing it. So he is working on a 60-hour mathathon, and not all at once. Let's be clear on that. It is, 60 hours on the clock, count down to when he needs a break, and then goes and takes a break. I believe he's also doing, overnight going to sleep and stuff, taking care of his kids. Minor details. I think he might actually have class too. He's a PhD student in mathematics. So, Zach was the host of the real analysis class that we just did over the spring semester, and we had a great time. There were like 12 of us in 2 separate sections. We had a good time with everybody. Also, Dawn is also on. And Dawn is yet another of our esteemed math streamers, a professional tutor from California. And Dawn does a lot of DayZ as well as mathematics streaming. So we do like to give our shoutouts and recommendations to everybody, so feel free. Go check that out. And if anybody's interested in signing up for the differential equations class, feel free. You're welcome, as long as you have had some decent understanding of calculus at some point in the past and could probably do some algebraic manipulation. You could be our people. If you would just like to join in and not have to, you have never calculused, you know what? That might also be a good class for me to do. I know several people have been interested in actually doing, actually teaching, Calc 1. As it stands right now, we are doing kind of a loose, loose conglomeration of calculus topics every week or two, Somebody will come around and ask, hey, what about this? So that might actually be my next project, maybe let's do Calc 1. But anybody is welcome to participate and sit around and heckle and whatever else. So if there's anything that you're interested in terms of what is differential equations, I would like an introduction, then you are welcome to definitely just come into the channel and take a look. I believe we're going to be doing Monday, Wednesday at 8 p.m. UTC, which is 2100 BST, and what does that make it? 1600 US East and 1300 US West. So whatever's working for you, that's the basic setup that we got. And if you just want to be like, look, Obi, just no, that's fine. I can respect that. But because we'll be doing Monday, Wednesday for like a dedicated class, then Tuesday is going to be our regular math stream, unless I'm not feeling it. If I am feeling like the ick, then I will probably bow out for the night and let people know on Discord or something that I'm not doing it. And on Friday we have our usual gaming sessions. Oh heck. So our community was also doing a good job, and we were gonna do those on Monday nights. So, ooh. Suppose I might be able to do it at 10 or 11 my time, because that'd still be 5 hours back as 6 p.m. and 3 p.m. for U.S. and everybody else is U.S. So, or Canada, U.S. time zones. Pens over there going, man, this is Canadian erasure. In lesson 2, when Jacobs goes over subtraction, he talks about September 1752, which has this really interesting story. Everybody's probably heard of it-ish, but this was the year that the Gregorian calendar was... nope. Hang on. No, that was 1582. Goodness. Alright, hang on one sec. You know what? Let's run a quick break. So... 1 minute. Be right back. Okay, we're back. So 17, sorry, what did I say, 1540 something, was when the Gregorian calendar was adopted. However, in 1752, it was found that the Gregorian calendar, in addition to the Julian calendar before it, and in addition to every calendar before that, had a bit of a problem in that the the original calendar only had roughly 360 days, and like they just start correcting stuff in terms of when the moon reached the same phase during the same season, and so it jumped around a fair amount. That's why, for instance, Easter jumps around quite a lot, because it's the first full moon after the spring equinox, or something like that, or the first Sunday after the first full moon after the spring equinox. Yeah, there is a nice progression to it. So the original one was like whatever the F you came up with. And then eventually somebody settled on 360 because, you know, it's a nice number. That was the Babylonians and things like that. They used 360 because they used a sexagesimal number system. Everything was based around multiples of 60. So 360 got really close. It didn't quite match, and after a few years you tended to notice. But, yeah. Alright, so then 365 was like Julian calendar, and then, like you said, somebody said, hey, wait a minute, that still is just off by like, so close. 360 no scope, yep. Yeah, the Julian calendar said every fourth year is going to be a leap year, so that should be fine. That'll fix it. Everything will be fine, except it wasn't, because eventually it still drifted just a little bit, because 365.25 days is still not quite right. But again, it's like it took hundreds of years to really notice that a huge amount, where it's like, oh, that was like a month that we just skipped. Yep. So eventually, Gregorian calendar was added in the 1500s, and like, okay, we're gonna fix this. Yeah, it's pretty close. And then again, in 1752, scientists figured out, no, we're still off just by a little tiny bit. So therefore, we're going to have 365 days in a year, except every fourth, where we have 366, except for every 100, where if it ends in 00, we will still have we will not have a leap day. Except on every even 1,000, where we will, again, have a leap day. So all of us, pretty much, I guess there are some people in chat maybe who have not lived that long, but almost everybody probably remembers the year 2000, where we were arguing back and forth about whether or not it should be a leap year. We did have a leap day in 2000 because it was an even 1,000, and so we accepted that. Yeah, it's gonna be. We're gonna have a leap day. Open set. Good evening and welcome again. 360 was right at the time until the aliens left and their gigantic ships imparted more angular momentum. Yeah, totally, 100%. No notes. Right? It only happens once every 1,000 years. It's pretty awesome. Now, granted, we're not going to see an even 100, probably, unless we've been uploaded to the cloud, I suppose. Asicon, you've played Soma, haven't you? No reason. I won't give away that one then. That's a good one, especially around if you like spoopy things around Halloween. That should be a good one. There's a lot of mind effery going on in that one. So yeah, 1752. They corrected it yet again by saying, okay, we need on September 1st, we're going to have a regular day, and then tomorrow, the day after the 1st of September, it is going to be the 13th of September. Although the University of Nottingham says that 2nd September would be immediately followed by 14th. So they might have done it slightly different in different countries. Or maybe this account of it is wrong. But either way. Some is the only horror game I ever loved. Yeah. So I played like a whole bunch of stuff. A whole bunch of horror games back in college, like Doom 3 and Fear, and there were a few more. And eventually I was like, I'm just not really into it. They're all like horror shooters. So of course, one of the objectively best game mechanics that they could possibly use is suddenly you've lost all your guns. And now you have to survive like wave after wave with only a knife, or just by running, or whatever. Or there's an enemy that your guns most definitely do not work on. Scotland took up the Gregorian calendar decades before England and Wales. Nice. I know I've asked you before, Asticon, are you down south ways? Or more the north ways? Midlands-ish. Yep, okay. Yep, we moved to Yorkshire. So, more north. Left of Bernoullis. Nice. The north. So I'm not going to get too much more specific than that, but I'll find you on Discord. We can discuss. There's also a Sensation is here, and is probably about 20 to 30 miles from where I am. So, pretty good. North Riding. Yeah, I don't even I need to figure out the whole geography thing. We've only been here for like what, 3 months, but has it been? Yeah. Yep. 2 more days and it will have been 3 months. Okay, well, that didn't help. I opened a bottle of red wine for some cooking tonight, and like, I don't drink wine, so I just threw it out with, or threw out a text message to my neighbors that was like, hey, you guys want this? And haven't gotten back. Yorkshire's big enough. Yeah, I mean, that makes sense. We had a few, like, really big counties. But, I mean, realistically, these days it's probably fine. They split it up more or less by, like, population and ease of getting from place to place. But New Hampshire, where I'm originally from, the, like, entire northern section above the White Mountains is Coos County. Sometimes also called Coos, if you don't know what you're talking about. But they also forgot the umlaut over the second O, so... So, yeah, Coos County was, like... There were only... When I was growing up, there were only 1 million people in New Hampshire. Like, exactly 1 million. Coos, as a county, had something like 30,000 people. Like, it was just a tiny number. Chaos, yeah. I didn't hear any jokes about it being chaos, but you know what? That makes complete sense. So, yeah, getting back to what I was saying earlier, like half an hour ago. Yeah, if you take any vectors and then decide to arrange them in whatever order you want, you will end up in the same place by adding all of those vectors. How you get there is going to be completely different, and it's going to be on the outer edges of this parallelepiped. So, it is... it's this beautiful symmetry which exists in mathematics. I'm definitely getting some Escher vibes there. So if you add your complex numbers, again, the result is the same, so they are commutative. But they are commutative by way of different things. And I mean, I guess it's kind of the same in terms of, like, real numbers, if you do it that way, right? If you do multiple layers, then you're going to end up with different ways of getting to the same result. So anyway, when we did this with lean, it asked us first, white screen, look out, bam. When we do it as an induction, what we say is, okay, we're going to try doing a base case, which is a plus 0 is going to be equal to 0 plus a. Is it true without using the definition of what we're trying to prove? So without using the actual a plus b is equal to b plus a, so without flipping anything, can we just prove that a plus something is equal to something plus a? Naturally, you just can't do it with like any old b, because we can't prove it. At this point, what we've done is we'd been able to say all of these things here. Add 0 and 0 add are going to be properties that we had. So 0 add said if we can... That's not popping up for you. Okay, cool. 0 add says 0 plus n is equal to n. So if you 0 add to something, then you're going to get that something. So that was something we proved a long time ago. And then here, add 0 is the reverse of that. So if we take a number and add 0 to it, it doesn't change that number. We still get that number back. So here we said, okay, a plus 0, we use add 0. 0 plus a, we use 0 add. And then that ends up with a equals a. We know that that's true from the very beginning. That was like the first thing that we were just allowed to have. Nasioma, how's it going? Good evening and welcome. So that was our immediate goal. And then we assume that a plus d is going to be equal to d plus a. And then we have to prove that the next number after that also works. So a plus the successor of d, which is d plus 1. Yeah. But we have special names for it when we're doing this stuff in what we call abstract algebra. So based on that, can we prove that? Right? Well, we said let's take a into the successor argument. So that means that the successor of a plus d is going to be equal to the successor of d plus a. We know that that is going to come from our goal, which again is unproven. A plus the successor of d is equal to the successor of d plus a. Also, for anybody who is going to be teaching mathematics, where you put vocal pauses is going to be super important. So, for instance, anytime that I have parentheses that I don't want to say parentheses around, I will include pauses to make sure that everybody understands what it is that I'm talking about. So again, this one up here is a plus the successor of d. This is the successor of d plus a. Opera GX sidebar is saying only 2 people are live. Oh no! Brackets. Yes. Yeah, I mean, parentheses really is like a statement of, or is a word that defines the statement as a whole. Yeah, it does. I've found that I need to refresh every single time I sit down. Otherwise, there's just all sorts of fun stuff. Parentheses. One of my colleagues called them parens, which is technically true, but really annoying. All right, whereas this one down here is the successor of a plus d, and the successor of d plus a. So it's much more subtle when I do it in class with actual students, but nonetheless, they tend to understand, like, oh, you're putting brackets around the particular thing by, like, saying something and then pausing. Like, yeah, that's how it works. So when we bring it into the successor, now they're individual arguments. We can say, hey, that's the HD that we set up here. We're assuming that a plus d is equal to d plus a, so let's just switch one, right? A plus d, rewrite the HD goal. Take a plus d and replace it with d plus a. Done. Successor of d plus a is equal to the successor of d plus a. And now that's just a reflexive property, right? It's the same thing on both sides. Cool, we're good. Yeah, I use round, square, and curly as much as I can. If anybody does have any actual questions, let me know. Because I will be happy to explain any sort of mathematics that you would like to know about. Certainly anything that I know of, I will be happy to immediately work on. If it's something that I need to research, or if I just say no, I'll let you know. Yes. Function array and object. Yep. Hey, that's perfectly fine. I was talking a bit about Jacob's elementary algebra and like some of the pedagogical stuff that he does, because this had originally caught my attention when I was enrolled in community college post bachelor's and needed to take a class called Reading in the Content Area. So our first homework assignment was go buy a book, like textbook, or find one. If you're working at an institution, go borrow one of theirs, because you technically should have one anyway. Go get a textbook, and then we'll figure out, like, how is it that we can figure out how to read it? Intermediate calculus or integral. Yep, there you go. Reverse power rule is fun. Yeah. So, when I'm doing this, I often will explicitly tell my students that I don't want you to do what the book says, which is like, okay, I'm just going to take this and say, okay, we divide by the new power to get x to the 1/3 and then plus c at the end. Like, that's all well and good, but it's also a pain in the ass. You're going to forget something. And a bunch of the students are like, I don't really understand. Like, I mean, I understand, but I don't, sort of. And it's kind of like, okay, just forget it, right? What does, like, this is like, okay, from a differential equations perspective, I am a differential equations teacher, and I learned, 5 different classes with differential equations in it. So, like, let's talk. I said, all right, looking at this as a differential equation, what would you like it to be such that you would get this at the end? Forget this stuff, right? The core, the kernel of this, the thing that we care about the most anyway, is the x cubed. Right, so that the ax to the n plus 1 over n plus 1 is kind of the standard way to do it, and that's how we got, this full result here. I tell them, all right, look, from a differential equations perspective, the most notationally nice thing that you can do for yourself is say, you know what I would really like? I would like this to be 3x squared dx such that when we take the integral of this thing, when we take the antiderivative, when we do whatever it is that you're doing here, we're just going to get x to the 3rd plus c. That's it. Now, you can't just make a 3, come out of nowhere. So, where did this come from? Well, you have to balance it. So, in order to balance this, we say, okay, we're going to have a form of 1, a third times 3, which is just 1. And then we take the 1/3 out because it's just a constant. And then that gets us our 1/3 on the outside of x to the 3rd plus c. Like stoichiometry, yeah. So Asticon, the good news is that it does what it says on the tin. It's an equation with differentials in it. However, if you don't know what a differential is, that's perfectly fine. The good news is it's super easy. It's this thing. Okay, it's all of our dx, dy, etc. What do those mean? That's also another thing, right? I'll get to that in a minute. Right, and then this thing, because we have this 1/3 as a multiplier, we can multiply it in, and we get 1/3 x cubed plus 1/3 times c, which is some arbitrary constant. But, in the words of George Carlin, when you think about it, right, 1/3 times c is also some arbitrary constant. So we shortcut this and say, look, I didn't really need the 1/3 to be multiplied by the c, so we're just going to make it c because it's just an arbitrary constant. Same would be true if this was like +1 on the end, or +7, -6, right? If there was another plus or minus just a constant on the end of this, it would get absorbed into this c, because c is just this vertical shift. So 1/3 x cubed looks, roughly speaking, like this. And then if we want to add c to it, right, that's going to take all these different values that we could possibly have for c, and wow. And then it would shift it either up or down based on what that value is. Any constant alone will just be 0 anyway. I meant specifically if there was like some other part of the problem that exists, like independent of the actual integral. Which, I mean, like, you shouldn't get that at all, ever. But I'm just saying, like, if it happened to be that, like, a constant is equal to an integral, and then you solve the integral and you get c, and then you have that constant over here still. Like, that constant and that constant can just be brought together and make a new constant. Okay. So in terms of, like, differentials, where does calculus come from in the first place? Right, so this is the story of one Sir Isaac Newton and one Gottfried Wilhelm Leibniz, or von Leibniz, depending on which translation you're using. Newton was very much a physicist and an applied mathematician, not so much a theoretical mathematician. He did not care if anyone else understood his work, because his advisor, the very famous Hooke, H-O-O-K-E, what was his name? Robert. So Robert Hooke was Newton's advisor, and Newton saw that Robert Hooke tended to advise his students on how to do something, and then when they figured it out, he would take their work and publish it with his own name on it. Phobos! How's it going? So, yes, very rude. Alright, and quick shout out for Phobos Stream. She was streaming earlier today, and if you have not been over there, she was doing some Tetris Attack, I think it was, the other day, and some math earlier this my afternoon, your morning. Yeah, no problem. I know, well, Zach sent me over, and then I was like, how do I not have you on my follow list? So very guiltily hit the follow button. So anyway, yeah, Robert Hooke was kind of a jerk, and Newton was not much better, but developed a few habits, one of which was deciding to take the... yes, I am in the UK now. Deciding to take all of his work and just basically have it kind of in stacks all around his room. Now, this wasn't necessarily this, like, squirreling behavior or anything, but he was kind of... he had this weird, just non-existent filing system, where it was just papers upon papers upon papers. And somebody would be like, hey, I need some help discovering, you know, some sort of relationship between these two things. And he goes, oh, yeah, I did something on that. Let's see. Yeah, here you go. Invariably, he would be able to produce a paper or, like, you know, series of notes that he would then give to his colleague, whoever it was, and send them on their merry way to study it. And he also never published anything, like, unless it was really, really big. But he never let Hooke touch his stuff, ever. He made sure that, like, some of the more major ideas were kind of in, like, a, not code, but sort of like they wouldn't be easily read by somebody who wasn't willing to spend hours upon hours working at it. So he would explain the idea to his colleagues, and the colleagues would go off and then develop their own work based on Newton's. And eventually at one point he said, okay, if we're talking about the motions of objects, and this was probably around the same time-ish as the Apple incident, which, for the most part, like, he didn't actually get clocked in the head by an apple, probably. He most likely just saw it fall, but nonetheless, right? He lived on an orchard, so... it was during the years of the Black Death. Newton moved home, and instead of doing work at Cambridge, he was doing work at his family's home on the orchard. So, much like the COVID years, there was a lot of sitting around and thinking. So, what... Why is that doubled? That's weird. No. No sloppiness. There you go. Alright, so, there we go. Nope. I want that one. Okay, there we go. Yeah. So what Newton thought about was the fact that if you were to look at a particle or an object or whatever that was flying through space, you'd have a particular location where this would be. Now you could call this XY, you could call it X, F at X, using a function notation or all sorts of stuff like that. You could label them with, because we want to talk about 2 points, we could label them with subscripts, which are just going to tell us this is the first, this is the second, right? Nothing super special about it. All right, and again, we could do the same thing with the function notation. Call it x1 f of x1, x2 f of x2, right? Or we could then list this as, okay, this is going to be our point, the like reference point that we want to talk about, x comma f at x. Right, so this one here, this one here, this one here. And then this other one could be, in terms of where we started, this has now displaced a certain amount in this particular direction. So h. And actually Newton probably would have used delta x, at least much more likely. And f of that following x, or the preceding x value, so x plus delta x. U. Alright, whatever. Now, when we're looking at this, what he was trying to do was trying to look at the velocity, which was the rate of change. I'll look at that in just 1 minute. In the position. So there's also this concept of rate of change, which we now know by the word slope. So the slope of a line, how steep is a particular line? Now we know it, again, by the calculation. M is going to be equal to, this was usually y2 minus y1 over x2 minus x1. It's also known as the change in your y value divided by your change in your x value, or the rise divided by the run, whatever you want to call it, whatever you're going to use there. Fembox Van, thank you. Do you think it would be a good financial advice? Financially a good idea for a non-traditional student to sit for A-level exams, probably math FM. I don't know FM. 1 or 2 other subjects without practice to try to apply and enter UK university after associates. Further maths. Okay. I mean, you might want to try like a practice exam or something. Oh, practicals. See, I mean, this is how little I know about the UK system. And those just naturally do not have practicals with them, or you're intending on doing something where you could have a practical but aren't. I don't know how any of this works. So okay. So we're also looking at this. We could then use the same idea for these other versions. So we could say, okay, this is f of x2 minus f of x1 divided by x2 minus x1. Okay, so looks kind of the same as the other one. It's just using f notation instead of using just y. This is good if you know what the function is. So if f of x were to be equal to, let's say, the square root of x plus 2 or something like that, this could work pretty nicely. Naturally doesn't have practicals. Yeah, okay. Biochem, physics have practicals. Makes sense. Math, econ, philosophy. Yeah. So yeah, I'd probably need more information to give any sort of advice, and I would take advice from, especially an American, with a grain of salt, but if it makes sense, right, that you would be able to do this and you're confident in those particular subjects, I mean, it might be worthwhile, or at least try one, like whatever you're most confident in, and see how you do. Spread them out. Don't do them all on the same day. Right, and that last one there could be done as f of x plus delta x minus f at x divided by x plus delta x minus x. This produces a very interesting result. It may or may not be able to see it immediately. So here we still have f of x plus delta x minus f at x. You're not able to just split this up and say like, oh look, the f at x's go away or something. Like, it's no. But don't feel bad if you did think that. It's just because you're not able to say that f is definitely a linear operator. So if it were a linear operator, then you could split any of the internal stuff up over this external stuff, the f that's there. But interestingly, down here, we have an x and we have a minus x. And we talked earlier about how addition is commutative. So we could switch the locations of x and delta x and end up with delta x plus x minus x. So x minus x is 0, and that leaves us just with delta x. Now this is still this stuff. It's just disguised a little bit. It's still talking about how much are you going up versus how much are you going over. Over here, we would have said like, you know, the amount that we're going over is this one, and the amount we're going up is this one. We can make a right triangle because these are orthogonal directions to each other. Right, this is our delta y, this is our delta x, and again, delta y and delta x are made up of the difference between their respective variables. Okay, so if we do this with various functions, and I usually do it with something fairly simple like a parabola, that one's kind of nice. If you do it with linear functions, it's kind of boring. It's like, oh man, alright. Mentioning commutativity but not associativity. Yeah, well, it's just because I don't put parentheses around things. How you doing, Maxie? Good evening and welcome back. If anybody has any questions, actually, let me know, and then we'll get back to stuff. But we're currently in the midst of explaining some of the basics of calculus. So Isaac Newton went through and said, okay, so we've got these functions, whatever they might be, f of x. We're going to talk about this in terms of the location we are versus the distance we have traveled to get to the next point. Again, delta x. And then turn and go in the orthogonal direction, delta y, to whatever y value or vertical value we have for the function. So these two locations. Oh, that's a shame. Okay. So if we do this function, actually, it's going to make it a bit harder. But let's go down here and say, okay, what we're going to do is we're going to say that f at x is going to be equal to x plus 2 parentheses squared and so the slope that we get, which is also known as the average slope, m bar, and meaningfully this differs from just the slope because the slope is a linear measurement. So if we're not on a linear function anymore, if we're on a curve, then we have to rethink like our vocabulary. So because it's on a curve, it's a little bit weird. It doesn't quite work the same. All right, so what we do is we say, okay, this is going to be f of x plus delta x minus f at x over delta x. This will always end up getting us the slope between the 2 points that we have on that curve that we have selected. And we could do this with like specific points, or we could do this with points in general like I've done here. So basically, this is what this looks like. All right, it's a parabola. It starts a bit to the left of the origin point. It's centered on y equals 0 at x equals -2, and then goes up and out like that. The distances that these have in either direction is always going to be 1 over 1 up, right? 2 over 4 up. It's totally 4. And 3 over 9 up. All right, the distances that we travel from our origin point are always the same as the original parent function, you know, y equals x squared. So in this particular case, it's slightly different, but realistically, it's the same stuff. All right, tell you what, I'm going to do a quick, I'm going to do a 3-minute break. I'm going to write out some of the algebra for this stuff, and I won't be explaining a whole lot until we get back. So now's a good time to stretch, make sure you got enough water, and whatever else you've got, snackage, meal, and we'll see you back in 3. All right, we return. And I completely... Oh, no, that one's fine. Never mind. It was this one that I messed up. This was 4x plus 4 delta x. Okay, and then at the end here we got x squared minus 4x minus 4 all multiplied by 1 over delta x. Okay, so the way this works is we look at first a reminder to any of the students who may have forgotten function notation that if we have f of 2, we take x plus 2 all squared, and we replace the x with the 2 that we had inside the parentheses here, right? If f of x is equal to parentheses x plus 2 squared, then f of 2 is going to be 2 plus 2 all squared. F of z is going to be z plus 2 squared, right? F of butterfly is going to be equal to butterfly plus 2 all squared. This is one of the fun things that we do in our class, is just like, hey, let's throw a random symbol in here. What does it mean? Oh, look, it's the same. Like, it doesn't matter what you put in there. It's just... Right, and then what we do is we say that our m bar is going to be equal to f of x plus delta x minus f of x all over x, delta x. We replace that x in the f of x with x plus delta x. So although it does have the same terms in it, which sometimes could be a little confusing, it's all right. It'll work out. So we say, all right, this is going to be x plus delta x plus 2 all squared minus x plus 2 squared. Yep. Emoji math. Right, all over delta x. Okay, so then I'm going to take this over delta x and make it 1 over delta x on the end. It doesn't really matter where or when or how we do it. Again, we're dividing by delta x. Just, I don't want to have to write a gigantic bar every time and then put delta x underneath it. It takes up extra space. I don't need to do that. So we said, okay, if we just take the numerator then, we're squaring this whole thing all together. So how do we square things? If we take some a plus b parentheses and square it, right, this is the same as a plus b times a plus b multiplied by itself. And then when you're multiplying these things out, my preferred method for students who are not super confident about this is we're taking something and we're multiplying it in. So take a thing and multiply it in. A plus b altogether times a plus a plus b altogether times b. Rinse and repeat. So we got the exact same thing going on here. We're just going to do that. This is going to be a squared plus ba plus ab plus b squared. And by the law of commutativity of multiplication, those flip around too. So a squared plus ab plus ab is going to be 2ab plus b squared. Is going to be a plus b parentheses squared. So how is that useful? Well, again, here we've got a is going to be x plus delta x, and b is going to be 2. So a, x plus delta x all squared, plus 2. ab is going to be x plus delta x times 2. And again, commutative law of multiplication, doesn't matter which order it's in, plus b squared, 2 squared. All right, minus parentheses x plus 2 all squared. So when you square x plus 2, multiply it by itself, we get x squared plus 2 times x plus 2 squared. What's that? Well, that's x squared plus 4x plus 4. And then this negative here ends up distributing throughout the entire set of parentheses. So we get a negative x squared minus 4x minus 4. All right, the first bit is not quite done, so that's why I kind of split that up. The first part says, okay, x plus delta x is now being squared. So it's x squared plus 2 delta x. I know what I said. Plus delta x squared. Plus, then this middle term here becomes 4x plus 4 delta x. So we got that there. And then plus 4. Down here, this is all just that stuff negative again. And now we get this nice little thing that happens. That subtracts out from that. That subtracts out from that. And that subtracts out from that. So those all subtract to be 0. Okay, well that means that m bar is going to be equal to 2 delta x times x plus parentheses delta x squared plus 4 delta x, all divided by delta x, which tells us if we divide each individual term by delta x, we get a 2x plus parentheses. There is 1 delta x left over if we squared it and then divided by one of them. I gotta move over. Plus 4. Yeah, too much writing. It's fine. Okay, so what this is saying is that no matter where we pick on this particular parabola that I wrote over here, I didn't need that much more room, right? No matter where we pick on here, if I pick this particular point at x equals 1, the actual point is going to be 1, 9. At x equals 1, if we just plug this all in, so m bar at x equals 1, it's going to be equal to, this is 2 times 1 plus our delta x. I'm sorry, I should have been more specific, because we're not there yet. Okay, x equals 1 and x equals -1. Classic mistake. Right, x equals -1. So what we're going to do is we're going to choose that x equals 1 is going to be our anchor location. This is where we're starting. Right, and then we want to go to x equals -1 as our second point. Okay, our delta x says how far are we moving to get from x equals 1 to x equals -1. We're traveling to in the lefterly direction, which is the negative direction. So that is delta x. Okay, so 2 times 1, the location we started at, plus delta x was -2 plus 4. So this says that the slope of that particular line is going to be 2 minus 2 plus 4, which is just equal to 4. So for every 1 that we travel to the right, we're going to go up 4. Or for every 1 we travel to the left, we're going to go down 4. Okay, because 4 is equivalent to 4 over 1 or negative 4 over negative 1. Whichever way you want to think about it, it's equally valid. We're all good. Okay, so this has a slope, again, m bar of 4. Right? So after we find this 4 for the slope, we say, okay, go to the picture, mark it at this point through negative 1 comma 1, and then that slope of that line that goes through the curve in these two locations is going to be 4. Now, Newton was not content with this. Of course not. Newton said, all right, what happens if I want a more accurate picture of, again, in this particular case, we're talking about like the velocity of a particle. If we're talking about an object that is being thrown in Earth's atmosphere, we have a very specific set of equations that can work out exactly where that thing is going to end up, neglecting air friction, after a certain amount of time or after a certain amount of movement in the x direction. All right, so thanks to Gravity, great band by the way, we can see what this pattern is going to be. So we have to do the same thing in terms of, like, if I want a more accurate representation of its velocity, the average velocity between negative 1, 1 and 1, 9 is going to be 4 meters per second, or whatever it is that we're doing. But if I want to know what the speed actually is, I have to do something else. Now your car is also working off of average velocity as well. However, the sample rate on a digital speedometer is like, 1 every 10th of a second or something like that. So it doesn't even matter in terms of like, oh no, it might not be accurate enough. It's accurate enough, right? There is no point at which you are going so fast, except on a high performance vehicle, that 1/10 of 1 second is not accurately reporting how fast you're going, right? Most of the time we go pretty straight and not speed up or slow down incredibly fast. Okay, so Newton said, all right, what if we want a more accurate picture? And the easiest way to do that then is to say, okay, oh, I have most certainly driven on the British country lanes. I had to go to Leeds to get my BRP. And coming from, again, elsewhere in North Yorkshire, it was like, oh yeah, I drive on this B road. I'm like, what? We're doing 60 down this little, like... I'm like, no, I don't like it. Okay. So again, we got this 1, 9 here. Oh, yeah. If we cut this in half and instead do a calculation on this particular setup, right, between x equals 0, and that was, by the way, that was within 48 hours of my arrival. So like April 6th, give or take. I don't remember when it was the first week we were here anyway. Oof. Yep. Okay, so this is 0,3. No, 0,4. Right, we're not that far off. All right, so yes, I was on the correct side of the road. Thank you very much. I did pass my road test after the third, fourth try, something like that. I was always getting it wrong on some stupid technicality. And the woman walks in and she's like, "Oh, yeah, yep, I can see why you would think that. Yep, try it again." I was one off 3 times in a row. No, it doesn't work like that. No, let's go. I have had this particular cough since I was 12, because my yeah, I would like new lungs, but it's actually I think it's the shape of my nose is such that everything just drains no matter what. So it goes and does the postnasal thing and then gets into toward my lungs wherein I cough it a lot. So there's not much I can do about it other than possibly get surgery to fix the shape of my face, and I don't want to do that. Now in this particular case, if we just want to even just look at it, right, we already know what's going to happen here. We're going a distance of 1 away to the right and a distance of 5 up. So guess what, right? Our slope in this particular case is going to be 5 divided by 1, delta y over delta x. Or if we wanted to prove it, right, we could do this as 2 times, let's do it the other way around. 2 times 0 plus delta x is 1. Right, and positive 1 this time. And x equals 0 is our initial value. And then plus 4. So here we get 0 plus 1 plus 4. It's going to get us our 5. Okay, so then Newton was like, all right, so what if we decrease that distance then? Instead of being at 0, right, we want this to be at 1,9. So right, this is our anchor. And we did -1, 1. We got an m value of 4. We did 0, 4 with an m value of 5. Okay, we need to move that down. What about 0.5 or 0.9 or 0.99 or 0.99999? Right? What do we get for all of those? So, first question is, what are the y values? We don't actually need the... okay, yeah, we need the y values. But actually, we don't need the y values. It's just for convenience in this particular case. So, it was x plus 2, right, and then square. So 6.25. 0.9, we add 2, we get 2.9, we square it, we get 8.41. 2.99 squared is 8.9401. And 2.99999 squared is going to be 8.99994000001. Okay, now everything is going to be anchored around this point, 1, 9. Hey Zach, how's it going? Apply to Oxford and teach philosophy of maths. Why didn't that lurk command work? Come on now. That should have worked. Oh well. Well, thanks for coming on over, Zach. If you need to hydrate and do whatever, feel free, because goodness knows you've been on for a long time. Alright, so the M bar that we had here. Yeah. The M bar, keep in mind, we found a way in which we could just do this in terms of x and delta x. So we no longer need to do this in terms of like what are the y values for each of them. So like this whole column here is technically unnecessary because we could just use x and how far it is away from 1. X equals 1. So here, right, we get 0.5 is a half times our 2 that we had. Okay, one more time. M bar is equal to 2x plus delta x plus 4. So make sure that that's there. All right, a half times 2 is going to be 1, and it is a distance of -1/2, -1/2, away from 1. So that's going to be again, 2 times a half minus a half plus 4 is going to get us a 1 minus a half plus 4. So that's going to be 4.5. Did I screw something up? Oh, yes I did. We're not at a half. Sorry, our x value. Right, the anchor point that we've chosen is going to be 1. So that's a 2. I was going to say, this should be increasing. Alright, so this gets us an M bar, a slope of 5.5. Alright, next one, 0.9. So we get a 2 times a 1 minus a 0.9 plus 4. It's going to be a 2 minus 0.9 plus 4 is going to be 6 minus 0.9 is going to be... Okay, again, how far is it away, not what is the value. It's a negative 0.1, right? Small. Oh, there's another one. So this is now going to be 6, 2 plus 4, 6 minus 0.1, so 5.9. Okay, what about 0.99? Again, same deal. 2 times 1 minus a 0.01 plus 4. It's going to be equal to a 2. Let's jump to the chase here. This is going to be a 2 plus 4 minus 0.01. So this is going to be 5.99 as a slope. And what do you think the next one's going to be? Okay, again, this is going to be a 2 times our 1 minus 0.00001 plus 4. It's going to be equal to, again, 2 plus 4 is 6 minus 0.00001. So this one is going to be a 5.99999. Okay, so the next question then becomes, what if we actually had our point at not just our anchor point, but the other point that we wanted to talk about, like our sliding point? What if we moved that back to exactly 1, 9? Well, if we moved it exactly to 1, 9, we've got a bit of a problem. Right? We would end up with a m bar here of... Well, actually, that's a lie. I can't go there yet. Going back to the beginning of the problem, we end up with m bar is equal to f of x plus delta x minus f of x all over delta x, but our delta x would be equal to 0. So m bar would end up being f of x minus f of x over delta x, which is a 0 over 0 case. Now this is very bad. Like, not only are you dividing by 0, but you're also... it's a 0 on the top. And the more you study limits in terms of like pre-calc stuff or in a calculus class right at the beginning, the more you will talk about how like we can't really look at a particular point, but we talk about what's going on with the behaviors around that particular point. So in some cases we had like asymptotes, right? A function goes like this and then shoots up toward infinity. If this is x equals 4, then what we'd be looking at here is, right, as x goes to 4, y goes to positive infinity. And realistically, we also have to say, from what direction is this coming? So as x approaches 4 from the negative side, which is what the superscript is going to mean, then y is going to approach positive infinity. This is especially important if you have something that's not the same on the other side. So like if we had one that came up like that, or just like spontaneously began to exist somewhere, right? Then we'd have to say, okay, we have to specify which direction it's coming from as well. Yeah, discontinuities. Right, so sorry. Anyway. Right. So then what we say is, okay, so 0 over 0 is causing two problems. Like this one right here is going to be a function that looks more or less like 1 over x minus 4, where if you plugged in a 4, you end up with a division by 0. It's not actually a problem that much. That should be negative now that I'm looking at it. Right, this isn't going to be so much of a problem in terms of like figuring out individual values and where it goes and all that. We'd actually, again, be able to say, as x starts approaching 4 from the negative side, we could say the same thing that we did over in this table over there, which is to say we could say it's going to be xy, this is going to be 4 is going to be undefined, right? We don't have an actual value there. And then we would start with like 3, 3.9, 3.999. We could find a bunch of different values and find out where this is going to based on the trend of how this is moving. So looking at the trends of what's happening over here, right, we're actually saying, hey, wait a minute, m bar is just going to be 6 plus whatever our delta x is. Right, now you could have seen that way back here when we were doing this part, right? 2 times x plus delta x plus 4. If x is equal to 1, then 2 times 1 is just going to be 2. And then we can combine that with the 4 at the end and then leave delta x as a variable, because we don't know where that's going to be. We don't know how far away we want to look. So here, 6 plus delta x is going to be our slope of the line that goes through those two particular points. But what if, Isaac Newton wondered, what if we took this and said, well, let's just do it at this one point? We actually got rid of our delta x way back up there. We divided it out. No, that's supposed to be plus delta x there. Oops. Not worth it. So that would mean again that our delta x is equal to 0, but we could just do that right here. M bar is going to be equal to 6 plus 0. It's just 6. And in fact, we don't need a bar anymore because it's not an average slope. This is actually the slope of the actual curve at that point x equals 1. Sorry, the slope of the slope of the curve at the point. Y equals x plus 2 all squared at this value, this point 1, 9. This is the tangent line, yes. So I sometimes avoid using the words just because it has like meaning to the students to be like, oh, the secant and the tangent. But yes. So realistically, you wouldn't say the slope of the curve necessarily, but the slope of the line tangent to y equals x plus 2 parentheses squared at 1, 9. Yep, so what we're doing now is we're saying no longer are we just going to be content with using secants, because secants will get you something that admittedly is going to get us closer and closer and closer to the correct value. But it's not going to get us the exact slope of the line that is tangent to the curve. It's forever going to be secants. So over here with all these, right, these are slopes. Of lines secant to y equals x plus 2 all squared anchored at 1, 9. It doesn't actually say it has to be anchored at 1, 9, but you get the point, right? It's going to be because I said so. So with this, right, slope of the line that is tangent to the curve at that point versus the slopes of the lines secant to this curve at all these various points anchored at 1, 9, right? These are two different things. So the slopes of the lines which are secant are, again, we take our function doing this. We find a particular point. This is, again, 1, 9. We anchor this here and say, okay, this is not going to move, but all the rest of our points are going to be drawn in, rest of our lines are going to be drawn in. Nope. Like this. So that this is going to go through here. Or this is going to go through here. Let's actually move. Harp, very nice. I was a trumpet man myself. I don't think it would quite sound the same. I mean, literally, but also aesthetically. Right, so over here, what we've got now is there is only one way in which this works. There's only one particular line which is going to have all of these properties. And it's that one. The one that goes through 1, 9 and has the exact slope required to touch only at this particular point on that particular curve. Now, it is true that if this like came back down or something like that, it would hit it again, but that's not the point, right? If this was a higher degree polynomial, it would hit it again somewhere, probably. But like I said, we don't care about this because the graph is like changing its behavior after the point in question. What we cared about was like, what's the behavior that's going on immediately surrounding it, right? Is there some neighborhood in which this is going to strike, you know, this particular function yet again because of changing the delta x value? I don't really know how to properly convey that, but right, we don't care about those pieces. We're just saying in this neighborhood around it, is there kind of like another point where it could potentially suggest that this is going to not be the proper tangent? Like I said, I don't have a good explanation for that, but we know that, for instance, like from trigonometry, if we have a circle, pretty close. If we have a circle, right, and we just draw like some line that's going to attach to it, right, this is a secant line. Oops. This is about as approximately close to a tangent line as I'm going to get. Right, and so like if we can agree that there is some common definition for tangent, that's probably good enough that I'm just not coming up with right now. The point is that, like, sure, there's a whole bunch of different lines with different slopes that, like, may never touch this curve a second time, but when it's anchored at that point, 1, 9, it is, locally not going to hit that curve again. There is one particular slope for which this happens. Okay. So Newton said, but now, what about finding this tangent of the, finding the slope of that tangent, right? We could then combine all of these pieces, and it ends up working out very nicely. What if we wanted to do it in general? Well, we did it already. It's up here. 2x plus delta x plus 4. Make delta x 0. Two x plus 0 plus 4 is 2x plus 4. This is now, right, our slope of the tangent line at any particular point along the entire parabola. Anywhere you want to pick, right? You want to know what the slope of the tangent line is going to be at, right, x slope of the tangent line, which is equal to 2x plus 4. I've seen this before. It's a nice, easy, it's a nice, easy linear function. There we go. Right, so like -4, -3, -2, -1, 0, 1, 2, etc. Okay, so -4 times 2 is -8, plus 4 is going to be 4. Right, and now I could just fill in the rest of it because it's a linear function. I know that the output here, m tan, is going to increase by 2 every time because the slope is 2. That's it. So 6, 8, 10, 12, 14, 16. That's not true. Nope. Hang on. Am I feeling okay? What's going on? Are we all right? No, that's -4. Okay, that's my problem. Yeah, so -4 times 2 is -8, plus 4 is -4. Okay, and then it increases by 2 every time. So -2, 0, 2, 4, 6, and 8. Syntax! How's it going? Good morning, good time zone to everybody. My name is Obi-Wan Pez, this is n-simplex Pachinko. We're talking about the invention of calculus at the moment. So if you have any other questions, let me know, and we can get to it fairly soon. Right, and we did find already that at x equals 1, the slope of the tangent line is going to be 6. We already knew that. Awesome. This ends up coming from slope of the tangent is going to be equivalent to taking the limit where our delta x from earlier goes to 0 of f of x plus delta x minus f at x all over delta x. So this part here is saying that our delta x, the distance between the 2 points that we were getting our secant from, is going to go to 0. So as it shrinks down, what's going to happen? And again, with a parabola, this makes this nice linear function that we get. And we saw earlier, right? That's this part here. We said we would get an overlap, which is just 0 over 0. That's a bit of a problem. But on the way, we were actually able to divide out our delta x's top and bottom, and then all we got left is 2x plus delta x plus 4. The delta x is 0, so it's 2x plus 4. That's it. This is Excalidraw, which is alright. It gets to have some finicky issues when you have multiple people drawing on it, which is also a possibility. I would say it is mildly better than mildly better than the Discord program that we were attempting to use, which would reset every half hour, something like that. That one hurt. And it is slightly different from Microsoft Whiteboard. Similar to, but legally distinct from. I don't think that either of them is necessarily going to automatically be better or worse. I was a little bit upset when I lost my license because I left my job, and all of my whiteboards on Microsoft Whiteboard were wiped out. So it was bound to happen. You can always use MS Paint. Danny Highway uses MS Paint and does just fine. Milton. Okay, interesting. So, Danny Highway is a streamer who has been working at Chegg, I believe still is there, and is also doing math tutoring on Twitch. So he also has a very unique perspective compared to a lot of us, hoity-toity theoretical type people. Mostly his attitude is I'm going to help you change the tire on your car, not I'm going to sit here and talk about how you need to have a spare. It's let's get what you actually need, in the short term, and worry about his spray can in your car. Yeah, usually that works. Yeah, no, I know. Run flat, whatever. Or tire goop? What was that? Forget. There was one particular brand that I sold at a hardware store. Okay, so this definition that we have here, this slope of the tangent line, is what we call the derivative. Okay, which we have several notations for. Isaac Newton used dot notation, which was fine until you started getting too many dots to actually be able to do anything with, and then Isaac Newton said, why would you need more than two? It has no meaning beyond two, so therefore we should only have two. Which, not only was it wrong, but it was just very wrong. So the amount of shock that's put on a particular item, let's say, a rocket that is coming back to Earth and trying to land itself on a platform, the amount of shock it receives is in fact the third derivative of f, right? Its position function, which is also called jerk. The fourth, fifth, and sixth derivatives of a function are similarly going to be the rate of change of those things. So the rate of change of the jerk is called snap. And then the two rates of change of those rates of change are called crackle and pop, which I am not kidding. It was the 1950s. Yeah. Yes, Asticon. I am not kidding, I swear. I can hear you laughing. All right, and then we start getting away from Isaac Newton, and we start talking about Gottfried Wilhelm von Leibniz, who was a math teacher. And in teaching math, he decided, you know, this whole thing needs a firm foundation on which we can discuss like a more robust notation for all of this. And so he said, you know what? We're not going to... he didn't, in fact, know anything about Newton's stuff because this was all independent. He ended up saying, okay, if I want the first derivative, we can either shorthand make it a hash, or that's not a hash, but a single stroke at the top like this, or we can say that we want the derivative of f with respect to x. So the derivative of f with respect to x, which is also going to be written as the derivative with respect to x of f of x. Or if we're doing partial derivatives, which is like a advanced calculus sort of thing, oftentimes what we do is we just say this is the derivative with respect to x of f. And if it's only a single variable function, if f is only on a single variable, then it's equivalent. It's the same thing. But usually this means partial derivative. If f has more than one input variable. So what I mean by that, for example, is like if you're trying to track the motion of... no, you know what? Let's just do that. If you're trying to track the motion of particles of air in a room, right? If you're trying to track the motion of particles in the room, then you have 4 variables that are going to be inputs. Three spatial, and 1 time. So, if we're going to have all of this stuff, and then we're looking at the rate of change, the partial derivative is going to say, you know what, rate of change in what direction? Because we've got 3 different directions to choose from, and then also time. So, like, how are we going to do this? So a partial derivative will say, okay, in terms of a time step, what is the change in its position going to be? What is the, essentially, what is the vector that this particle is going to have at this particular location, at this particular time? Yes, partial differential equations. Yep. So, differential equations as a whole is a field in which you are looking at what are we might have, for instance, a set of very simple rules that govern the rates of change of stuff. So, for instance, a spring mass system. If I just take something, I don't have a spring. Why don't I have a spring? If you had like a slinky or something that had a weight attached to it, and then you start like bobbing it a little bit, right? You notice how it's going to move. There is a very simple set of differential equations which tell you the rates of change of the position and of the velocity of that thing, given its like initial motion and what kind of spring you have and how heavy the mass is compared to it and all this other stuff. So it gets a little complicated, but it's not too bad. Partial differential equations start talking about, okay, now you've got particles in a room, and we know the motions of those particles based on like an airflow that's going on. So you've got a fan in this part of the room that's going this way, and we're going to make it time invariant. So it's always just blowing in this particular direction. What is the eventual motion of the particles in the entire room, given just the blowing of this fan and the dimensions of the room and all that stuff? You could figure it out. It's complicated, but you can figure it out. You would most likely need a computer to do almost all of them. Some of them you can do by hand, but they are a very few and usually the simplest cases. All right, so Leibniz says, okay, we need to explain all of this stuff to students. So these notations are more robust in terms of being able to describe what's going on. Again, he didn't know anything about Newton's work, allegedly, but I believe him. And there. In theory, he probably did mostly this, but like, I don't know. There's certain lines that I don't, they're pretty blurred. I don't know exactly who created what, but yeah, whatever. Nonetheless, Newton did this. It was just in some form or another. It'll be in Principia Mathematica, I'm sure. I gotta see if the library has a copy. Because if I'm right, they've got a copy from like 1800s. That'd be pretty cool. Not 1600s, but you know. So people started learning about, this is like one of the very few things that Newton actually published. He did so at the behest of one Sir Edmund Halley. Yes, that Halley of Halley's Comet. Because Halley had come to him and said, look, I'm working on trying to describe the way in which the orbital mechanics work in the solar system. And Newton was like, oh, yeah, I got a thing on that, hang on. And he looked for it and he couldn't find it. He's like, tell you what, give me like a week. And he worked for like a week and then gave him a treatise on exactly how the calculus worked. I am not kidding. That is not just old person speak. That is what it is called, the calculus. And when he gave it over, Halley was like, well, okay, this works perfectly. Have you published this? And he's like, no. And he's like, dude, get on it. Like, you got to publish this. So eventually Newton published, and it became Principia Mathematica. It became one of the most one of the most printed books like in all of mathematics. The only ones that definitely beat it are going to be Euclid's Elements, which has been compiled into a 13-book version all 13 books of Euclid's Elements. Um, and the only non-mathematical book to ever exceed Euclid's Elements in printing is the Bible. At this point, I have to ask which Bible, but yeah, it doesn't much matter. It's all right. I'm gonna cycle some water, running out here, so I will be right back. Probably grab a snack. Good time to stretch, get up, do all that stuff. So I will be back in 3 minutes. See you very shortly. Thanks so much for sticking around. Hey everybody, thanks for sticking around. Got some beautiful tiger bread that we picked up in a little town in North Yorkshire called Pateley Bridge. So if you ever make it up that way, they have a wonderful set of bakeries, and there is a specific place that I don't know. Should I? Whatever, I said it. It's not like I live there, so there's a very nice little coffee shop that is called Coco Joe's that sells hot chocolate slash like coffee mocha. And they have like chocolate from all over the world. That's like, I don't know, 13, 14 different kinds. And they just give you like little wafers and they're like, yeah, sure, just try some. And then once you decide on one, you could be like, all right, I would like a mocha, or I would like just a hot chocolate made with this particular chocolate. And so it's really good. This was the bakery at the bottom of the hill. Pateley Bridge is one gigantic hill. So if you go, make sure you drive carefully. I was also told, do not bike into this place, because apparently somebody was riding their bike somewhat recently and ended up getting hit, and it was pretty bad. Righto. So we get the derivatives of a particular function, which again are going to be dealing with, as you said correctly, Asicon, yep, the velocity, acceleration, jerk, and then snap, crackle, and pop of a particular object. When other people started collecting Principia Mathematica, and then eventually on the Germanic side collecting Leibniz's work, they invariably sort of worked their way into France, where they were talking about things at conferences and all this other stuff, and they were like, hey, have you seen this? Yeah, I've seen that. Oh, it's by somebody else. And they were like, oh, well, that's a little confusing. So they started arguing about who was, the superior version and whose was done first and things like that. Lock and drop. All right, cool. All right, Lezioma. So people started arguing about whose was better and whose came first and things like that. Eventually, they decided to settle things, and Leibniz said, okay, I'm going to write to Isaac Newton and try to understand how all of this worked. And he wrote to him, and Newton was like, yeah, I figured all this out years ago. And Leibniz was like, okay, but I published it. And Newton was like, yeah, I'm in the process, but I figured it out. And so Leibniz was like, okay, well, other people want to know, so we're gonna, get this figured out and send it to the Royal Society, and the Royal Society will adjudicate, whose discovery came first and whatever. And Newton was like, I don't think you want to do that. And Leibniz said, all right. Think I do, but all right. So Leibniz takes the journey and eventually gets all the way over to England. And when he gets there, he goes to his appointed meeting with the Royal Society, and sitting at the head of the table as president of the Royal Society is one Sir Isaac Newton. And Leibniz says, "Oh, scheiße." So Leibniz states his case and lets everybody know exactly how it was that he had independently discovered the calculus, and tried to figure out how how derivatives work, and like all of the various little properties that work within their discoveries. So, you know, the simple stuff first, the algebraic, the super simple algebraic stuff that we were talking about earlier, you know, commutativity and associativity and things like that. And then they start getting into various other properties that they themselves discovered. And Newton also had talked a little bit about like what he discovered and when and how and all this. And Leibniz then went on to describe how he also worked out integral calculus. So it's not just derivative calculus like we see here, but also how to reverse the process. That's what we did up above. The differential equations that were used for solving a lot of the Newtonian problems were actually discovered at the same time as derivatives, because it was just, well, you take your derivative and you reverse it, and it becomes the original function it came from. So the context is really important here, syntax. It's it's not so cut and dry in terms of like the, of course I didn't label these things. That's Calc 1. Yeah. Boo. I want the differential equations one. It's also possible that it's just in my gray notebook. Just like Newton. No, there it is. Bottom of the stack. Not so much. Okay, cool. Oy. Alright. Not that one. Oh, really? Alright, good news, bad news. No, it's just all bad, pretty much. So I have one of these composition notebooks where the first, like, 5 pages are, like, dedicated to historical context of differential equations. The bad news is I can't actually find it, which is too bad. But basic idea is that, I already said it, the differential equations were discovered basically at the same time as differential calculus. It was just that they weren't like formalized as a particular system by Newton at all. It was pretty much like, well, here's what we're going to do, and then we're just going to back it up. You we have a differential equation, and then we're just going to magically, not magically, but we're going to do this thing and turn it back into its previous original equation that it would have come from. And so Newton was able to discover the reverse of integral calculus, i.e. The reverse of differential calculus, i.e. integral calculus, through a bunch of, like, if we're in this situation, this is what we do. If we're in this situation, this is what we do. And Newton basically only came up with solutions of the form y is equal to a function of x, or y prime. And, right, like, since this is Newton, you would have just put y dot is going to be a function of x. Y dot is a function of y. Newton's cooling equation is that one. And I think that might be it. Whereas Leibniz did those as well, but then also worked out how to do stuff that was of the form... nuts. See, this is where I need my notebook. And it may actually be here still. The problem is that I have no idea. Oh, haha. Well-worn computation notebook. Chapter 1, differential equations. Yes. So, from a historical perspective, okay, so Newton had stuff of the form y dot is f of x, y dot is f of y, y dot is f of x comma y, where he had some series solutions, so numerical solutions, which are perfectly valid. All right, I'm not going to harp on it. For f of x comma y being of the set of polynomial functions. So, you know, he didn't do any work with, let's say, you know, logarithms or anything like that. Especially since they came in later. Like, he basically had no work on logarithms in the first place. But yeah, so he worked out this series of solutions where f of xy was a polynomial of some kind. Oh, am I wrong? Did I just screw that up? It's possible. Oh no, Napier was earlier. Yep, that's fine. Never mind. No, I just messed up. Yeah, Napier was early 1600s, so I was only out by 50 years or something. No, that's 80 years. It's fine. Oops. X times a partial du dx plus y times partial du dy, which then eventually gave way to partial differential equations. So equations that are of this form in PDEs are actually super easy to solve because they all have very predictable solutions, and the methods by which you do it only work on these particular things. So it's fine. Leibniz ended up doing like all of this same stuff. He wasn't able to really figure out, well, he didn't do series solutions because he didn't need to do numerical solutions. He also figured out, we're not going to do y dot for him because he came up with a much better notation for it, right? This was dy dx is equal to f of x, dy dx equals f of y. So Leibniz developed what's called separation of variables as like a method of solving differential equations. So in separation of variables, basically what you're doing is your goal is to get whatever you've got on the table to look like f of x dx is equal to g of y dy. And this is really where differential equations starts. Because what we're looking at is now we have these differentials, which are going to be the little tiny pieces, the infinitesimals, that tell us what variables we're working with. Now, in some other contexts, this could have also been, because it's equivalent, f of x is equal to g of y times dy dx. This is 100% the exact same thing as the differential equation that I wrote first, this one here. However, I much prefer this because, again, it separates our variables apart from each other and says, like, all the x stuff's over here, all the y stuff's over here. Not to mention, when you do this and then say, I'm going to now take the antiderivative, take the integral of this whole statement, we've got our integral with the dx on the left, we've got our integral with the dy on the right. We don't have to change anything. We don't have to add anything. We don't have to make something just pop out of thin air. So, as we would here, for example, where we would have to say, oh, well, if I want to take the integral of both sides, this has to then be dx. So we'd add in a dx seemingly from nowhere. And it really bothers some students. I'm okay with it. The bothering the students and also the other part. That's fine. So the Royal Society convened and listened to the arguments, and eventually it was decided. There was a big, 40-page report on everything that said that joint credit would be given to both Sir Isaac Newton and to von Leibniz for the discovery of differential calculus, because they both worked out seemingly independently without contacting anybody else. They both independently discovered the same stuff. So congratulations, you both get joint credit on this. And sole credit was then given to Leibniz for his discovery of integral calculus, because Newton had never done literally anything in terms of trying to find notation for figuring out how to solve differential equations like this. I mean, I agree. Just means of the. So sole credit is given to Leibniz for his discovery of integral calculus. And then on the cover of the report is the decision of the president of the Royal Society, a cover letter, if you will, that was from the president of the Royal Society, one Sir Isaac Newton, who went on a scathing rant about how awful it was that this whole debacle should even happen in the first place, and how dare this plagiarist come all the way to England from Germany and, disturb the Royal Society and do all this, that, and the other thing. So, yeah, Newton went on a very angry tirade about how von Leibniz was a plagiarist and ripped him off completely. And it's pretty plain to see that they were pretty much independent of each other. Like, Leibniz wrote Newton a couple of letters, and Newton never told him anything. So, how would you even think that you gave him information? So Leibniz went back to Germany and decided to just be a teacher. Just focus on teaching his pupils everything that he had learned, including the calculus. But specifically not getting back into math research for new stuff, which is really too bad. But he was also late in the game at that moment, so. Newton, on the other hand, went on shortly after that to attempt to use mathematics to prove the existence of God and to work on alchemy. So you can imagine how that went. Hey, Red Tree. I mean, if you're still getting paid and working on impossible problems. I have some other interesting notes about other people who were in differential equations at the time, or at least for the next couple hundred years beyond Newton and Leibniz. Oh, yep. Oop, I left out a couple of things here. Leibniz also discovered how to reduce homogeneous equations which are those which equal 0, into separable ones. And also solved first-order linear differential equations. So, complete solution of those that look like p of x times y prime plus q of x times y is equal to r of x. So he was able to generalize the solution for all of these, which pretty impressive. Most of the time it breaks into like, oh, it's just separation of variables. Other times it definitely does not, but it gets really, really close. Isn't it everyone's dream to start going on delusional tirades and getting paid for it? I mean, yeah. And one of the most famous problems that existed at the time, solved by neither of these two, but definitely used by them both as like an example of something to do, was called the brachistochrone problem. Alright, you have a particle at A which needs to get to B as quickly as possible. So how do we minimize the time that it'll take to get from A to B? I mean, in theory. So both Newton and Leibniz worked on this problem for a long time and couldn't figure it out. And two other people, Jakob and Johann Bernoulli, ended up working on this problem as well, trying to work on differential equations. Jakob was actually the one who was working at the University of Basel in Switzerland, studied differential equations and engineering as his primary research area, and coined the term integral. Both Jakob and Johann were complete jackasses, a bit like Newton, but fortunately less steely than Hooke. Maybe not quite as stealing averse as Newton was himself, but they fought with each other like all the time. And then they also loved to fight with their students. And it was usually attributed to like extreme ambition that the two of them had, had this kind of quarrelsome nature. So The good news was that anybody who studied under them was like really super good mathematicians. And that included, after Jakob died, Johann took over the professor position at Basel. He taught his son Daniel Bernoulli, and Daniel Bernoulli is the guy who came up with the solution to, or came up with the Bernoulli principle, which, if you know the basic idea, if you have a wing, like on a plane or something like that, usually. What's happening here is a bunch of air is coming in. At a wing. And the air that's going underneath the wing here ends up attempting to escape as fast as it can, but it ends up creating this like massive high pressure front. Because all of the air that's going underneath the wing is stacking up in this area, this very tight area. So it creates a high pressure front. Whereas, if you notice what's happening up top, right, we've only got this little bit here, which is going to go like that. And if we keep, you know, the same actual spacing and everything, this is kind of leaving a gap here. So it won't, in fact, leave an actual gap. It'll start pulling the air that's completely missing over the top down to try to compensate. You know, the universe is not trying to do anything, it just does. Alright, which creates a massive low pressure front up above the wing. And in order to attempt to compensate on that and return everything to an equilibrium, then there's going to be a force that's imparted that's going to be at right angles to well, the pressure differential and all this other stuff. So oftentimes what happens in the space above is you end up with like little eddies of air circulation because it's trying to like fill in back on itself, but it can't. And so it pulls more and more air from above, leaving again this low pressure front, whereas underneath you have a high pressure front. It tries to fill the space, sucks the wing right into it. So Daniel Bernoulli obviously did not do this with airplane wings because airplanes did not exist at that point. He did, on the other hand, have like differently shaped objects that he put into a river, and like the force that was grabbing it and taking it away from him was the force that we see here, the lifting force on the wing. It's the same thing. Right? This happens in any fluid, and both air and water are fluids. If you actually did this in a river, it'd be kind of interesting because in the high pressure area, you'd actually notice that the water level would start rising, and in the low pressure area, the water level would start sinking. So even in, you know, a standard river that you might come across, if you stick an object in that's like this, you'll actually see water stacking up and sinking away in those places. It's also like if you have a rock in a in the middle of a river, like, you know, whitewater rafting or whatever, you can also see the same phenomenon. Anywhere that there's like high pressure, so the water is hitting the front of the rock, it's mostly going to stack up and go over it, or stack up and go around it. And then on the bottom side of the rock, even if like the water is more or less flat-ish, if the water is moving fast enough, it'll still have a depression after the rock. Anyway, the Bernoullis both worked on the brachistochrome problem as well, and they were trying to minimize the time that it'll take to get from A to B. Numbers of people have tried, like, oh, well, what if you just make a straight line, right? Then, well, this is going to have to spend time accelerating, and it doesn't go as quickly as it possibly could. So somebody figured it out that like it would be best if we start accelerating faster at the beginning, and even if we have to like come back up, it'd be better than trying to like go straight from A to B or any other version of this, right? If we made this almost flat, that would take forever to get started. So like that was a non-starter. But people said, okay, if we use gravity first, use gravity first, and then when it gets to the end, it'll slow down a little bit, but it's still actually going to be faster because it'll be going so much faster as it gets lower down. All right. Now I can't remember. I mean, it must be Euler, right? Oh, nope. Okay. It was Johann. Yep. So the guy who took over at the university demonstrated that the brachistochrone solution is a cycloid. And easiest way to make a cycloid is if you have some sort of circular object. You put an object on the end, and then it will trace out as it's moving. It will trace out a cycloid. As it reaches the bottom, do you know how you would simulate these? In theory, you could do it on Desmos, but like, I don't know how. I know that a bunch of like the learning management software oftentimes has like an applet inside of it that'll do all these fun demonstrations. Programming? Yes, at least I could get the like numerical values for it pretty easily. But essentially it's a set of parametric equations that are on t, time, and it's something like a plus I mean, I should just look it up. Yeah, trace the particle. r times t minus cosine t. Nope, it's sine. Damn it. R1 minus cosine t. Right, or in polar, oh, I see. No, that's fine. Whatever. So that's actually the same thing that you use in polar. You just put thetas instead of t's. Woo. And then one of Johann's students was, in fact, Leonardo. Naturally came up with all of the amazing things that we attribute to him. Discovered the value for E, and came up with so close, Zach. So close. Came up with e to the I pi plus 1 is equal to 0, which we and he would probably know it more clearly as e to the I pi is equal to negative 1. But this one does have a certain elegance to it, being that it encapsulates all 5 of the biggest natural constants in mathematics and brings them all together. So it's pretty cool. Euler went blind during his tenure, the last 17 years of his life, and dictated all of his research to students on the calculus variations. So that's where you were talking about that one. Yeah. Did a lot of work with partial differential equations and multivariate calculus, as well as series solutions and everything else, because this guy did not rest ever. Oh, yeah, and he formalized all of algebraic notation into what we use today. So it's been like almost 300 years. It's fine. Let's see, and then we had the two major Frenchmen who were in on this. Joseph Louis Lagrange succeeded Euler as chair of mathematics at Berlin Academy in 1766, showed that the general solution of an nth-order linear homogeneous differential equation is the linear combination of n independent solutions. We will talk about that if anyone is interested in my differential equations class. We're going to be starting next week, right here, on Monday, the 8th. Absolutely. So I have a whole section on Penn Center's Discord, which talks about the differential equations class. If anyone is interested in joining the class, It's not like I can give you credit or anything. I am not an accredited institution. But if you're at all interested in just having some fun or hanging out or discussing mathematics at probably a bit deeper of a level than most people are used to, could be just my pedantry, could also be that, I've taught it several times, so a little bit of both. Anyone is welcome to like just hang out anyway, but if anyone wants to be like on stream, we will be like meeting in the Discord server, securing rooms during that time slot, which is going to be same as what we do here, probably 9 to 11 BST, which is 2,000 hours to 2,200 hours UTC, which is, if we go back 5, 16 to 1,800 hours US East, and that would mean 13 to 1,500 hours US Pacific. So all the mental gymnastics. So like I said, I put all that stuff in there. If you're interested in just like hanging out, that's perfectly fine. If you're interested in participating, let me know, and type something up in Discord. It'll be fine. I do recommend that anyone who wants to be like on stream has a fairly good calculus background, just because you will definitely need Calc 1. Probably need like Calc. It'd be nice to have Calc 2. Probably not absolutely necessary, but having the like alternate integral methods is pretty useful. So integration by parts, partial fractions, series solutions, things like that are going to be very helpful. And I keep forgetting which one was the one who did Napoleon. Did stuff with Napoleon. That sounds wrong. Nice. Yep, I also independently discovered the change of base formula when I was in my pre-calc class. So I was, 16 or whatever in school, and we were talking about all of the rules that were being used, and then I was like, wait, if I just change this around, and I think I was able to, or I think what I did was I took a log statement, I backed it out to an exponential statement, and then I just used a different log to redo it. I was like, that's the change of base formula, or I was like, this is really cool, I can change a base. And so I told my teacher, and she just smiled, and she was like, great, show it. I was like, all right. So like I taught that lesson. And this is me as a high school student who, at that point, I was intending on going into physics. Like, not teaching, just physics. Life kind of changed there a bit. Not like a huge amount, but and then nope, it was the other one. Anyway. Wow. Okay. Yeah. The thing. And then time came for the unit test, and I was flipping through the pages and got to the last page, and the second to last question was prove the change of base formula. And I just stopped and I blinked a couple of times, and then I looked up at the teacher and she's like, I was like, all right, I got it. Yeah, I mean, everything's different, right? Yeah. I absolutely hated her after another month or two, but nonetheless. we did trig, and then we were doing a problem which involved trying to deduce what would happen, or what's the equation of the behavior of a pendulum on a cuckoo clock, which when the weights get all the way up to the top, right, it stops the gears from connecting. So the gears will disconnect each other, or disconnect from each other, when force is applied here. So like a gear in here will disengage from the other gear it's usually attached to. Right, so as there is more... Oh, that's wrong. If that one's at the bottom, whatever, it's fine. Oh, I'm sorry. It's the other way. So when this one reaches the top, it hits here, it applies a force upward, and it disengages the gears from each other. So they're backwards, but whatever, it's fine. Hey. That's not what I... There we go. Oh no. So anyway, this disengages the gears, and then the cuckoo clock, the pendulum, starts free swinging. So it'll normally go out to about here and here, right? But then as it swings back, it's only going to swing to about here. And then here. And then here. And then here. And it becomes a little more pronounced as we go through. But like the point is that all of the x values that we end up finding for these particular locations end up shrinking in down toward the center until eventually we get this. And then it will, within the realm of physics, it'll actually stop. But within the realm of mathematics, it technically does not stop. It just becomes imperceptibly small. So this was the cuckoo clock project. We were determined to figure out like how this was going to work. We got toward the end of the project. It was probably March or April. And like a number of people really did not have it, and we kept asking questions, we kept trying to figure stuff out, and we were all just so mad about this particular project. And a number of us got C's and D's. And we're like, I can't figure this out. And then we were told not to use calculus. And then, like, the one kid who did use calculus got an A. And now, granted, he might have done it another way first and then shown that in the report, but nonetheless. And the other, like, absolute genius kid who is now, I don't know, director of some project. Last I knew, he was working in the clean room at some big tech corp. He's probably managing the whole facility at this point. But anyway, he was like absolute genius level, and he ended up getting a D because he used calculus, but I suspect it was probably because he used calculus and didn't explain it a different way. So like our entire class complained to the department manager, like tried to figure out what it was that was just not working and try to get our grades rectified. The teacher was like, no, like you can maybe try again, I guess, or like have a little bit of an extension, but please, I'm not just gonna change your grades. So Lagrange also did linear homogeneous differential. Oh, it's already said that. Variation of parameters, which is like one of the most important methods of solving differential equations. It's super powerful, but if you have the wrong kind of equation, it's going to take forever. And Pierre Simon de Laplace was from Normandy, and then went to college in Paris. He did gravitational attraction, was like his major thing. And ironically, because Lagrange is the one that the points are named after, he figured out a particular integral transform, which allowed him to find like solutions to integrals that were really, really difficult. If you just change them into a completely different form, solve them, and then bring them back, it manages to like do something. You find actual solutions. And so Laplace found the transform in 1782, but Oliver Heaviside, yes, that is his name, was the first person to realize how they could be applied to differential equations, which wasn't until like 100 years later. And then Laplace was also the one who was famously tasked by Napoleon Bonaparte to come up with like a theory of the universe in order to say like how differential equations and mathematics kind of like inform all of what we know of the universe. And when he got published and handed Napoleon a copy, he read through it and then met with him at a dinner party somewhere and was like, you know, I noticed that you didn't thank the Almighty Creator at the beginning of the book. And Laplace goes, I didn't really need that hypothesis. This was not actually a statement of like profound atheistic tendencies. This was just that this was a science book. Like, I didn't need to assume God in order to do the science for the rest of the entire book. Like, it was a science book. But yeah, talking back to the Lord Emperor of Europe. To get back to your question, syntax. So, hmm. Oh, actually, yeah, I also, it was only a few years ago, I guess, 5 to 10 anyway, that I also, as a teacher, mind you, proved all of the log rules, because I was like, look, I've been sitting here telling students that these are the log rules. Let's really go, like, all out and get down to base level understanding of, like, what is it that we're actually talking about here? And I was able to say, okay, logarithms are exponents. So if we go with the assumption that logarithms are exponents, then what consequences can we create to find the proof of all those log rules that we just know exist, right? So we said, okay, if we have log base b of x plus log base b of y, right, then what are we going to get? Again, assume that I don't know what these are going to be. Maybe we just do this anyway. So we get this, right? And I said, okay, let x be b to some power, so we just call it m. Let y be b to some power n, right? This is true. X and y can be rewritten as powers of b. It's just going to be more difficult because we don't know how it works. Okay, so then this is going to end up being, right, log base b of b to the m plus log base b of b to the n log base b of b to the m times b to the n. Alright, well, that's nice and easy. We know how to deal with that. That's log base b of b to the m plus n. And actually, I think we can leave the other side exactly as it was, like without changing it over. So this is still x and this is still y. Right, so if we just move the right-hand side, this is going to be log base, well, we already got that. This is saying log base b of whatever is asking the question, what is the exponent, the logarithm, on a base of b that is going to get me this stuff? So if we're asking, okay, log base b of b to the something, then this is just going to be m plus n. So what exponent on a base of b gets me b to the m plus n? Well, it's m plus n. Alright, is all that log stuff. Is equal to, what's m? So m can be equal to, we come back up here and we say, oh, well, we need to rewrite these then. X equals b to the m is going to be equivalent to m is equal to log with base b of x. And n is going to be equal to log with base b of y. guess we could have done that up here in this and just called this one m and this one n on the next line, and it would have been proven there. But nonetheless. Alright, so log base b of x plus log base b of y. In this particular case, you don't move the left-hand side, which some teachers really still prefer. This one's going to be log base b of x plus log base b of y. Ta-da! Okay, now to get back to your other question. So time period of Calculus 1, right. So typically, the way that it works in American schools, we've got K through 8, usually, is just going to be math. It's pretty much done, almost always, either with your class, just as your class, or it's done with a peer group who are broken out as being like of your ability level, whatever it might be. 9 is going to be algebra. And this is like the introduction of variables, solving equations, some light statistics. So typically in there is also like, oh yeah. K through 8 is usually 5 to 13. How old did I turn in 8th grade? That was 14. Yeah, 5 to 14. Give or take. I think 5 on this one's kind of low end, but nonetheless, that's usually how it works. 9 is going to be your, again, 15-year-olds. All year. No. You're in it for the year. Geometry. (11) is going to be Algebra 2. Which for me meant matrices, systems of equations, linear programming, things like that, typically advanced topics. And then 12 is when you turn 18, so this is your last year of high school. Is like functions and trig or pre-calculus. So I had a student who griped about this. She wasn't actually my student, but we were like, she was running the club that I was sponsoring, so like we spent a lot of time together, and she started griping about pre-calculus, being that it's all just like this hodgepodge of random topics that either weren't covered or were covered at, were already covered in Algebra 2 or whatever. I was like, no, it's just not. Like, the functions portion of pre-calculus is specifically getting you to understand that, like, the rules are the same no matter what kind of function you're using. It doesn't matter if it's one of the functions we already used or a completely unknown function. Like, the rules of functions are the same. The rules are the same throughout the whole thing. And then trigonometry, obviously. We did a little bit of trigonometry in, like, geometry. But this is starting to talk about, well, how do we build how do we build this trigonometry? Yeah, the days are split into periods. Usually, when I was in it, and this is some number of years ago, man, my junior high and my high school years, which were 25-ish years ago. Whoa. Right, so big old grain of salt right there. For about 25 years ago, our typical day was broken into 8 periods of 44 minutes each, plus 5-minute travel. Alright, we also had one, like, homeroom period where you just went to some random stupid classroom that was assigned by alphabetical order to make sure that you were there. I absolutely friggin' hated homeroom because there was this one kid who was just a complete dipshit. Like, in middle school, he brought a taser. And then lunged at somebody. Because that was fun. I'm just like, nah, I'm out. Like, I don't need to be here. Yup. One of the little handheld ones, yeah. Meant to take 2.5 periods. Completed all exercises. Bit over 2 weeks. Yeah. If you're motivated, right? About 10 to 20 years ago, there was a push to move to 4 periods a day of about 90 minutes each. And this was called block scheduling. And then typically you'd have like an A day and a B day. Yeah, I mean, like, I liked it when I was teaching it because it gave me more time to actually do stuff. At the same time, like, oh, that was the other thing, was that these were A and B, whereas the, like, 8 periods, these were daily. So you had every class 5 days a week. Didn't matter what it was. With the exception, I guess, of, like, your extras, like music. No, music and band we had it every day, but like physical education, health, certain other classes we didn't have every day. What was your motivation? Apart from just getting it done. Or dealing with the awful teachers. So he didn't make it and you wanted to one-up him. Alright, it is 1 o'clock in the morning here, so I think I'm gonna get going, but we will hop on over. Let's go see Dr. Gold. He is doing SAT practice and more tutoring stuff, so... Oh! Oh, 3 in the morning, man. I'm so sorry. Good luck, Syntax. Alright, so we're going to head over to Dr. Gold's. In addition, Dr. Gold is one of our math chads. Anybody who has not followed all of these delightful people, please do so, because we are the main 7 who do math education streams on a regular basis, and either we are educators ourselves or tutors, so like also educators. Yeah, I mean, that's true. And you're in Finland, so that's like, oh, you might not be in Finland anymore, I guess. At any rate, okay, yeah. Dawn does math. Zach at e to the 2i pi, Penn Center, who again has our Discord server that we usually use. Ian Stuckey, Obi, that's me, and Simplex Pachinko, Danny Highway, and Dr. Gold at Actual Education. So, yep, from Dawn's, yep. Yeah, sauna nut summer. Alright. Well, thank you everybody for coming. My name is Obi-Wan Pez. This is N Simplex Pachinko. I will see you all later. Thanks so much for coming. Have a good night.